And Carl Williams is from NIST. He's acting director there, and he will tell us about quantum sensing and imaging from the lab to I didn't get the from the lab to near-term commercial applications. Sorry. So Carl, if you could go on full screen mode so we can then see your presentation. And thanks a lot for joining us at Quantum Industry Day in Switzerland. I remind again the attendee to ask questions in the question and answer at the bottom of your window, and so that we can ask the question to Carl after his talk. So Carl, the floor is yours.
Thank you, Jacques. It's a pleasure to be joining you this morning. I hope everybody can hear me, and I will get started. So it's my pleasure to be here and join another industry consortium along with its academic partners to talk about what's going on. And so I was asked to talk a little bit about sensing. So I want to give you a perspective of what's going on in the US with regard to sensing. So I'm going to start with the landscape and give a few words about what NIST is and all. And so, you know, I look at the landscape, and I want everyone to understand that it really is long term. I mean, to build a generalized quantum network like Wolfgang was talking about is something that's probably 20 or 25 years out there. In part, quantum networks are difficult because you have to miniaturize a lot of components. You need to make them cheap if you're going to really build a quantum internet or a broad quantum network. But if you look at what you can do today, of course, quantum key distribution is there. You can do quantum measurement. Some quantum sensors are out there. But, you know, the computer is way out. Has a fair amount of complexity and other things. But there's a lot of other things that you potentially could do. And one of the things I want to talk about is quantum networks for relativistic geodesy. And I will get back to this toward the end of the talk. But relativistic geodesy is about studying the breathing modes of a planet. And I will come back to why this is important and how one might do this. I also will point out, you know, if you can really make this stuff cheap, you can put it into a smartphone and everything else. You know, I know there's this billion-dollar market out there of quantum games. Why? I can create correlated randomness between perhaps 100 people and ensure that a game never plays the same way twice. And that correlated randomness will be used if it's cheap enough to create new kinds of games that don't play the same way twice. So this is the landscape as I see it. And, you know, it's going to be fun watching the next 10, 15, 20 years because a lot of this stuff is going to begin to happen. So what is NIST? You know, we are a national measurement institute. So our corresponding lab in Switzerland is METIS. And, you know, we are a national measurement lab. We're bigger than most of them. We do have a very broad basic research all the way to delivering state-of-the-art measurements across the field. And so very, very broad research portfolio along with a bunch of services. So in the lab that I am the deputy director of, we set the definitive US standards for nearly every kind of measurement employed in research and commerce. And to do this, we see ourselves as a world leader in the science of measurement, and you know, the quantum world is really key to how this happens. So let me give you a little history of QIS at NIST, so you understand where we're coming from before I come back and talk really about sensors in a broader aspect. You know, at NIST, we call the power of one quantum bit an atomic clock, and we have been manipulating these kinds of systems for 70 years. So we know how to do this very, very well. If you look at the definition of what a clock is, it has to be based on cesium atoms. Our cesium fountains are accurate to have an uncertainty of a few parts in 10 to the 16th. And so the blue dots are basically microwave standards. The red dots are basically optical. And sometime in the mid part of this decade, we will redefine the second. That will be done under international agreement through the International Bureau of Weights and Measurements, or the BIPM in Paris. And you can already see that when we do that, the frequency uncertainty will drop by more than almost 2 orders of magnitude, because there are now a number of clocks that are just a few parts in 10 to the 18th. And I suspect in the next year or two, there will be clocks demonstrated at a part below 10 to the minus 18th. Now, I talk about clocks not only because they're the power of 1 qubit, but because they are also increasingly sensors. So I'm going to show you some data here from a paper in 2010 from Dave Weiland's group. And this is basically aluminum ion clock, in which the aluminum ion is basically controlled by beryllium ion. I show this for several different reasons. One, this is a quantum logic clock. So we have been using quantum logic effectively to run one of our clocks for more than a decade now. And what I show you on the left is that that ion is in an ion trap. And if you start exciting the motion in that ion trap, the clock would tick differently. And that's nothing but special relativity. I'm seeing the motion of the ion. Now, again, the ion ain't moving fast, but I can already see the effect of the motion of the ion on the tick rate of the clock, as shown by those little red dots on the left. Then I go over to the right. And here I took that clock and I jacked up the table 30 centimeters using hydraulic jacks. And all of a sudden, the clock is again ticking at a different rate. See the blue and red dots on the right. That is general relativity. It's the gravitational potential. The clock has changed because I jacked the table up, and as a result, it ticks at a different rate. This is data from a decade ago. Today, we can see less than a centimeter in our best clocks. And increasingly, they will become more and more accurate. And in fact, these clocks are becoming so accurate that running them on Earth is not the best place to put them. They're too sensitive to everything from black body radiation to motion to everything else. We really would like to put them in a better environment in space. I will show you another of the devices we built at NIST. This is a chip that has 300,000 Josephson junctions on it, the same kind of things that are used in building quantum computers. Why? That chip basically then acts as a voltage standard, because this is the Josephson effect. And then I show on the right quantum Hall resistance. So what I'm showing you is that if we look at the best standards that we have today, many of them are built on quantum effects and are crucial, even if they're doing classical things, are crucial to giving us the best measurements in the world. NIST is also starting back in the early 2000s, went about after doing one of the early demonstrations of QKD and one of the first high-speed transitions of QKD, decided that we wanted to go see if we could build single photon detectors that were both number resolving and single photon sensitive and 99% quantum efficient. And we have done that. We have built 2 types of sensors, transition edge sensors and these nanowire detectors, both of which are now in the high 90% in quantum efficiency. So again, these were crucial because the better your detectors are, the farther you can stand your photons in a QKD system. Here I show what happens if you take a laser pulse and you put it onto the transition head sensor. And if you look at that first plot there, the n equal 4, 1, this is a mean number of 4. The brightest line is the 4 line, but you can see 3, 2, and 1 below it, and you can see 5, 6, 7. That's Poissonian statistics of a laser, but it shows you that my detector can actually see how many photons are in the pulse. It's really quite remarkable. And again, it shows you what we can do with these kind of devices. Similar technology that coming out of NIST has been put in to the Atacama Cosmological Telescope that basically measures the polarization of the background radiation in space. So again, it shows you how sensitive these detectors are and all to light, even out in the microwave. And this is quite remarkable. And I want to show you one final result here. Again, this is an experiment that's now more than a decade old too. Notice I'm not showing you the latest results coming out of our lab, but I'm showing you what you can do. So this is a game of using rubidium vapor to create squeezed light. And then we took and we created an entangled image of two cats, pixel by pixel entangled. And again, you know, this is quite remarkable. Today, you can get above 10 dB in squeezing. But, you know, these are hard experiments and are getting key to devices. So there's a lot that can be done. Clocks are sensors, and I'm going to come back to this. You can do all kinds of game with light and everything else. So what I want to do is I really want to talk for a few minutes about what's out there and what's going on, so that you understand the full realm of the world. And, you know, you can do basically sensing, imaging, and metrology. I'm going to give you an example in what follows of magnetoencephalography. I showed you about how you can use this to do pixel entangled images. I've talked about time. I've talked about the volt and a few others. So you really can do applications across the whole space. You really want to see what you can do in the sensor arena. This is a wonderful review article. It has a lot of things showing you how different qubits can be used and what they're being used for, typical frequency range. And I'm not going to go through this table, but I wanted to give you this reference just so you have it, because if you really want to dig deep into it, this is a nice review article that kind of shows you the whole state of the art across the field. So NIST basically in 2003 went to take our atomic clock, which was a big tabletop of things, and turn it into a chip scale device. I talk about this in part because it shows you it can be miniaturized. Very, very expensive to do this, but we miniaturized an atomic clock, and it was put in a package, and it's now sold by Microsemi. Today, there are other clocks that are being miniaturized that will be even more accurate than the one that is pictured here. And of course, optical clock miniaturization, especially if you're willing to go to something like a 2U rack, is also underway. So let me give you a few examples of what's out there. And I want to note that when I mention a company or anything else, it's not an endorsement. It's just an example that is out there. I want to give it to you because there are some remarkable things out there today. So like I said, if you can take these technology and you can begin to miniaturize it and drive the price down, you will eventually end up with something like the quantum internet that Wolfgang was talking about. And if you look at at magnetometers, a clock is nothing but a magnetometer if you put it on a magnetic sensitive transition. You can also build such devices out of nitrogen vacancy centers, silicon carbide, and the previous technology was built out of squids, which again are Josephson type effects, superconducting quantum interference devices. Now, I mentioned this because I want to talk about atomic magnetometers for a moment, because there's a really wonderful example of the benefit of atomic magnetometers. So these magnetometers I'm talking about were built by a company called QU Spin. The actual sensors were built by QU Spin, which is a Boulder spin out from NIST. But they were then bought by a company called Circa Magnetics and put into this cap that you see on the left. And I really encourage you to go look at Circa Magnetics, because that cap is what a modern magnetoencephalography system looks like. And unlike the old squid-based device, it doesn't require you to sit. You can be on a bicycle, you can be moving around. This is important because one of the things that people want to use magnetoencephalography for is to study people who have epilepsy. And they don't like being confined, they don't like being positioned, but being able to study them may help us come up with better treatments for them. So this is a system that is being built. It's currently state-of-the-art, probably quite a bit cheaper than what the old DC squid system was. And this is only the second generation of the device coming out of QU Spin. There are plans for a future generation. And so this shows a lot of promise and may have big impact on neuroscience. You know, there are studies out there talking about what the market will be for quantum magnetometers. And so here's an example of one of these. Again, nothing endorsed by NIST. This is just a market study, but it shows you what the state of the art is and the commercial application space. If you want to go to a larger device, you go see the kind of a system that atom interferometer that is in the lab of Mark Kasevich at Stanford University. And there are a number of these kind of devices. This is one aimed at looking at Einstein's equivalence principle and seeing that it holds at the highest level of precision. So these are really, really very, very precise devices. The footprints, as I showed you, can go from something that's very small with numerous devices on a skull cap to something as large as this. There's another program underway in DARPA, the Defense Advanced Research Projects Agency, that really funded the initial CSAC to build a 2-photon microwave clock. And we also have efforts underway at NIST to build a 2U unit of an optical clock that probably will have an accuracy approaching a part in 10 to the 16th or better. So efforts are underway to miniaturize these devices. Again, they're key and crucial because I've already showed you how they are sensitive to both motion as well as gravity. So I want to come back to the CSAC again. Again, as Wolfgang talked about, you want to build a quantum internet, you need to build miniaturized devices. And at NIST, we have been working on this now for a few years. We created a program called NIST-on-a-Chip, which is aimed at taking the best measurements we can, miniaturizing them, putting them on the chip, because if I can integrate them together and put them out in the field, then people don't have to send me their devices to calibrate. I can provide a calibrated source in the field, whether it's in an industrial setting like an auto manufacturing plant or LiDAR on a car or other things. So we want to put the best measurement we can directly on a chip. And we've been doing this for a while. We build these suites of quantum-based measurements that are self-calibrating, fit to function, manufacturable, and can be moved out in the lab. And I want to give it some examples of this. Again, there are putting cones on chip, putting graphene quantum Hall devices on a chip, creating, again, very small devices for atoms with their magnetometers or clocks, DC voltage, measuring electric fields. Again, you know, if you would ask me 10 years ago, can you go measure an electric field? You know, measuring electric fields was hard, but with Rydberg sensors, you can do this. And also measuring temperature using quantum optical mechanics. Again, a device largely used today for doing transduction between signals at between, say, optical and the microwave region. But using the same kind of device, we can also measure temperature. I want to go to one final thing. We learned a lot about using atoms as that an atom, you can see an atom can be impacted by light because when it absorbs a photon, it takes a kick. That same effect can be used to basically measure, become a radiometric sensor on a satellite. And again, this is important too, because, you know, part of the problem with climate change is that when we put detectors and things up on a spacecraft for 20 years, they tend to drift. And so looking at measurements over long periods of time on a satellite is really a hard problem. And yet we're coming up with technologies that we have demonstrated and put onto a CubeSat that basically shows that we can recalibrate things in situ, in space, so we know what the absolute absorption is. And that's very, very key to making better measurements in space that can lead to even more accurate measurements relative to climate change. So I talked a little bit about clocks, magnetometers. What I want to do is I want to come back to clocks and to relativistic geodesy, because as we're finishing up, I want to talk about where we can go. And again, you know, the best clock we have today is a Fermi degenerate clock. This no longer shows 1 over the square root of n, where n is the number of atoms type scaling. It shows 1 over n because the atoms in a Fermi degenerate clock are forced to tick synchronously, not as n individual qubits, but as n single atom qubits, all completely synchronized because they're in a Fermi degenerate gas. This is really quite remarkable. It's one of the best clocks we have out there. It is kind of key. But we have also gone to where we, using combs and other technology, either through fiber or space, to compare our clocks. We have a number of optical clocks, some of them sitting on the University of Colorado campus in the lab of Juni, others sitting on the NIST Boulder campus. And we can now compare these clocks next to each other using this frequency comb and look at the tick rates. And so we can make the best relative measurements of clocks and see how they tick with regard to each other and do time transfer at a few parts in 10 to the 18th using in the optical mode, something you cannot do with microwaves because of multi-bounce patterns in the atmosphere. But if I can do this, in principle, I can then take 2 clocks at a distance and I can entangle them. And I already showed you my clock is sensitive to micromotion. So I take 2 of these clocks in a long baseline interferometer and I put them out along the San Andreas Fault in California, a fault known to cause major earthquakes. And if I have a number of them and I have them beating together, I can watch the micromotions along that fault. I can watch the stress develop along that fault at a level of accuracy that is really state of the art. And so one day in the future, I may be able to make a prediction 2 weeks ahead of time of a major earthquake coming. One of the most destructive earthquakes perhaps to ever hit the earth. Why is that 2 weeks important? That's what it would take to evacuate the Bay Area and save millions of lives. This is where quantum technology is going. But I can also put it in space and use it to look for dark matter or gravity waves of very, very heavy objects, far heavier than what LISA or the current gravitational wave devices, Virgo in Europe, can see. So if you really want to look at some of the most basic pieces of the physics of the universe, it'd be great to put a couple of these clocks out in space, preferably at the Lagrange points. Entangle them, put them on a long baseline. I can create an optical telescope that way. I can perhaps see certain types of dark matter, especially some of these very, very light forms, these axion type dark matter. And perhaps gravity waves as well. So the future is really very bright. I hope I've kind of given you a view of what one can do. And with that, I'm happy to take any questions.
Thanks, Carl, for this enthusiastic talk. It's more in my field. I loved the way you show finally that the development of atomic clocks 30, 40 years ago until now, and we see what we reach. We have product on the market like miniature atomic clocks. We are using the extreme stability of the clocks for measuring, as you said, perhaps earthquake at the micrometer level. And this is just amazing. And also to be able to measure things in space, like for the LISA mission, gravitational waves. And there I can just comment on the fact that the collaboration between Europe, Switzerland, and US happens. So for example, CSEM is currently characterizing the laser developed for the LISA mission by NASA. And this is a very well example of this kind of collaboration. Now I will go to see some questions from the audience. And we have one from Hugo Lehmann from the Swiss NIST, META, so in Bern. So the question is, beyond optical clocks, where do you see the application of quantum sensing in fundamental metrology?
So I actually see it in numerous ways. And again, a lot of the applications will be in the classical realm, but they will be using all the techniques that we have developed in the quantum realm. Again, a clock just measures time. I mean, the second is really not, doesn't really require superposition, doesn't really require entanglement. So I see it in clocks. I see it. I see it in temperature. I see it in if I can take the technology that gives rise to the volt and to quantum Hall, and I can integrate onto a single chip. If you have two legs of V equal IR, the Ohm's law, you basically can build a fully calculable, scalable electrical device to measure any of the electrical properties. And of course, also single electron transistors, which are again key technology to certain kind of solid state quantum computing effects. So, you know, I really think that the quantum is going to come in on all kinds of metrological applications across the space as the technology builds out, becomes cheap and robust.
Okay, thanks. Perhaps we take a last short question, but we will have again some time in the panel discussion to continue discussing. But I have one here, atomic clock miniaturization. How much effort in time and manpower is this a way to move basic research to industry?
So again, the CSAC was a program that DARPA had a number of programs on. It cost several $100 million to do that. And a lot of it was cheap, making the lasers robust, cheap, small, stable, everything else. So the cost of doing any one of these things at the moment is hundreds of millions of dollars. But, you know, because the technology is so far out there, I think you're going to see it happen. You know, the cost of building a quantum computer is going to be billions of dollars. So we are spending the money necessary to make this technology robust and packageable. And so I think it's happening. Again, you see this with the detectors and the sources. It's just going to take time and a lot of very smart people and a lot of good engineers.
Yeah, this I completely agree with you. So I think lesson learned from the atomic clocks, it takes time, it's costly to miniaturize, to take the cost down of all these components that will be finally integrated in the quantum network. So thanks, Carl, again for your answers, and we'll be back in the panel discussion afterwards.